have the last talk of the workshop, which is going to be given jointly, right, Anthony? Both of you? Yeah. It's going to be a joint talk between Antonio Frisoli and Massimiliano Solazzi from the Scuola Superiore Sant'Anna in Pisa. They're going to be talking about how to use wearable haptic devices in the context of applications to improve manipulation capacity.
Thank you very much, Miguel. So last but not least, we are going to focus again on wearable haptics, fingertip haptics. So I'm just going to recall some, this work was made in Scuola Superiore Sant'Anna. I'm Antonio Frisoli from the PERC laboratory. And in this talk, we are focusing again on fingertip and the wearable haptics. And we will recall some concept, and we will analyze a device that can render cutaneous feedback at the level of fingertips. So this is a table that provides you a picture of the possibility to provide haptic feedback. Of course, we might use the mechanoreceptors that are in the skin in order to provide haptic sensations. And this is a way that we are interested to analyze. A second way is also considering with traditional kinesthetic device, the articular joints, or also other kind of device like tendon vibration can be used to stimulate muscle spindles in the muscles in order to provide, in this case, proprioceptive feedback. And then, of course, we might also provide some vestibular feedback in order to provide a sense of motion to the overall body. So we are interested in the cutaneous part since, as Domenico was saying, this allows us to go wearable. That is an important requirement. In terms of fingertip, if we think to strategies to provide haptic at the level of the fingertip, I like to divide this in three different categories. So one category is to exploit the properties of surface haptics. So this is particularly relevant where you are in contact with the surface. Typically it's a planar surface, a glass. So there are different concepts. These are just the main ones, like the squeeze film effects, electrostatic attraction, or time reversal wave focused by Vincent, that can be applied in order to provide fingertip at the level, feedback at the level of your fingertip. But this requires a surface for the interaction. A second way is that of, so basically these are the three concepts I was explaining before. A second way is what I call embedded haptics. So that means that you have a tool in your hand, and then you provide, these are some examples from William Provencher works, where you provide a skin stretch on a handle that is grasped by the hand. So basically, in this way, still you have haptics at the level of your fingertips. Another way is to use vibration. But you need to, again, having something in your hands. What we like to analyze as a concept in wearable haptics is to have your hands free. You have timbals on your fingertips. So you might have multiple fingertips interacting with an object. And in this case, we provide haptic feedback at the level of the finger pad that is very rich in terms of mechanoreceptor. So being focused on this concept, over the years, we have developed different prototypes, analyzing different ways on which you can implement, actually, practical way to implement this kind of feedback. Basically going from one finger to multiple finger device. So the idea that we have in mind is that you can see here a user that is immersed in a virtual scenario simulation in a cave that is interacting with the virtual world. So this is actually how it is in the reality, and this is what he's seeing. And we can make him having a real feeling of touch of this virtual object. So in this presentation, we will analyze in particular two main streams. Okay? One stream is based on the rendering of shape geometry, what we call, we can call also contact location. We have also two different prototypes showing this concept. So in terms of contact location, we can provide perception of different curvature, different surface, by exploiting the fact that we can move a small plate and put this plate in contact with your fingertip. Another way is that of exploiting the concept of skin stretch. So we can, consider a single point of application, we can render a force. And this might be interesting to provide force feedback like in grasping manipulation scenarios when you want to simulate the grasping of an object. So I will focus before on this rendering of shape geometry. We'll show some previous results, and then my colleague Massimiliano will show the latest results we had. I like this distinction that before Vincent was making about basically the geometrical properties, the invariance, geometrical invariance of a surface that can be used to generate feedback. In particular, the position is when you have a large surface and you do kinesthetic feedback. Then first order and second order properties are basically slope and curvature. So we, of course, in order to provide position feedback, kinesthetic feedback is the best one. While when we are dealing with slope and curvature display, since you are doing small movement, I mean, to having an estimation of curvature, you can even do a small rotation of your fingertip. Cutaneous feedback can play a big role. So we conducted in the past some experiment to characterize slope and curvature perception by using fingertip displays. So this was a first device. Basically, as you can see, this was based on the Vincent Hayward work, where we can exploit the rotation of a plate to provide the illusory sensation of moving on a curved shape. So basically, the fingers is moving on a on a line, but since the plate is changing orientation, we can provide the illusory feedback of moving on a curved surface. So this is the first device that we built in 2007 that is not very portable, but is small enough. And this was mounted on a kinesthetic device. So we were able to test what was the effect of cutaneous and kinesthetic and both. And in particular, this is an example of how the device was operating. So when the user was moving, the cutaneous device was rendering the orientation of the surface, while the kinesthetic device was providing the force. And you can see here more in particular what is the actual movement. If we consider the rendering of second order properties of geometry, in particular curvature, we found out that basically we can improve by combining cutaneous and kinesthetics. So in this column, we can improve the discrimination, so we can reduce the threshold of discrimination of curvature. So we are better in discriminating a curvature when we provide not only kinesthetic, but we had on the top of this also cutaneous feedback. And so this was a first result. But of course, this is still not a wearable device. Then we work in order to implement a more wearable device. This was the first attempt with a voice coil actuator. And the device, it was able to orient a plate and provide a contact location on the fingertip. And we also analyzed the concept of slope perception. So not curvature, but we were considering the capability of judging the parallelism of two surfaces. This is the first order property. So it is interesting to see that, of course, what we found is that the best performance that we achieve is that when we combine the kinesthetic and the cutaneous feedback, and that the kinesthetic has a better performance than the cutaneous in the discrimination of parallelism of two surface. But what we found that was interesting is that if we analyze how these sensory modalities combine in perception, basically they can be explained according to a Bayesian model of perception. So they combine in such a way that the sensory modality that has the high reliable measurement has an higher weight in the final perception of the shape. So what happens basically is that when the surfaces are very close, the cutaneous is more reliable and plays a bigger role. When the surfaces are very far apart, the kinesthetic plays a bigger role. So basically, cutaneous in perception slope improves the overall perception of shape. Then I leave the floor to Massimiliano that will show you the latest development in this area.
Yeah, okay, thank you. And yeah, I will focus more on the design of the latest devices that we developed in our institution, taking into account the results that we had in the psychophysical experiments. So before, we start on the newest device for us, for the rendering of force. So that is a device that can render the direction of the force, its intensity, and even can render the displacement of a tactor. So it has been designed with the aim of simulating the physical interaction with virtual objects by replicating the skin stretch at the fingertip that have when I grasp an object, and even to render the contact-no-contact transition, so the discrete information when I suddenly touch something. And for doing that, so we need 3 degrees of freedom, and one translation it is perpendicular to the finger pad for contact-no-contact and force, and 2 translations that are tangential to the finger pad. So by an engineeristic point of view, so if you analyze the requirements, so the criteria for design such a device in the best way, so of course we have the wearability that we already know the requirements after this workshop. And so in this case we have, we can say an isotropy, so that means that all the degrees of freedom in this case have similar requirements as speed, force, and mechanical bandwidth, and so on. And we need only small displacement, because to stretch the finger, to deform the finger, or to apply force, we don't need a large workspace. So that brought to our design choice for this device, for this type of render, that is a parallel kinematics that allows us to pack all the actuators at the base, that in our case it is the back of the finger pad, and then to have the kinematic chain with the light and thin links in order not to have two bulky parts in the bottom of the finger pad. So this is an overview of the kinematics of our device. It will be presented at this conference more deeply on Tuesday morning, so I will be really brief. So it has a 3 RSR spherical rotational joint with a mixed motion of the end effector, that is the kinematics and the action of the forces. With this mixed motion of the end effector allows the tactor to rotate around the finger pad. So you can see the orientation, different orientation of the end effector, and while we will focus only on the translation of the end effector, because as I say, I just want to apply a force on the finger pad. And so this is the device specification that we obtain with this device. So you see that is even by the pictures, it is quite enough to be weared on all the fingers. Now it is just on this position with 2 fingers. And the maximum displacement from one point, from the point of contact, is 4 millimeters, so it is enough for stretching the skin with a maximum force of 5 newtons and a weight of only 22 grams. So we started on validating our device before with an experiment on the distinction of different the force direction. So we performed an experiment for distinguishing 8 different directions in 2 different conditions. One with the low normal force, in such a way that at the center point it results with a certain slippage of the skin tactor in respect of the finger pad, and then on a higher level with a higher level of normal force, such a way that there is always a stiction between the tactor and the skin of the finger pad. So we obtain 2 confusion metrics for the stick and the slip conditions, and we found that well, it is our device is in any case achieves a good result in providing information about the direction of the force, and there is a better performance from this preliminary. It is a preliminary test, of course. There is a better performance in the stick condition than the slip condition, and of course, as I anticipated, it can be used in a dual end configuration for manipulating objects in virtual environments. So in the video you can see a user that is manipulating cubes in a virtual environment. Of course, just for sake of making the video, there is a 2D representation, but usually you can see in a 3D video. And from this point of view, you can even see the tactor that is moving, applying the force that the user would feel moving actually the object in the real world. So in a task, we measured the force, the grasping force that it is needed to lift, to manipulate the objects with certain weights. And in this case, even in this case, in 2 conditions, one with only visual feedback, and the second condition with even the force feedback by the device. So in this case, we saw how we expected that the normal force with the visual haptic condition, it is lower, and so that even this is the relationship between the 2 forces. So just to prove that the adding, as we expected, that adding the haptic feedback helps the user to modulate the right amount of force for lifting the virtual objects. Then, so now focusing on the other kind of devices that we want to develop. So the device for the rendering of shape and geometry, so curvature perception, parallelism perception, and the rendering of the contact plane, the contact plane tangent. So we developed this new device that is pushing toward the wearability of our previous devices. And in this case, even in this case, we analyzed, as before, the design requirements, and we found, of course, the wearability that we already know, and then, but we found different requirements in this case. In fact, in this case, we have different requirements between the translational degrees of freedom for the contact-non-contact transition and the rotational degrees of freedom that we need to display the orientation of the plane. In fact, in this case, we need a larger range of motion for the rotational degrees of freedom. So in this case, our design choice, of course, it is different, even if the device has, even in this case, 3 degrees of freedom, and the overall dimension is almost the same. So now we have a serial kinematics, so with 2 rotational axes, and then a translational axis at the end for applying the force on the finger. And in this case, we we have the actuators that are not located at the base, and each joint has a different has a different actuator. So in particular, so we have 3 degrees of freedom kinematics that allows the accessibility of the detector to the whole surface of the finger pad, so a really wide range of motion. The actuators are located at the joints. For the first 2 actuators, so the rotations, we have DC motor with a spur gate transmissions, and for the last degrees of freedom, we have a voice coil actuator. And so here you can see the different degrees of freedom of the device. So a fast rotation around the axis of the finger, then a rotation to an axis perpendicular to the finger, and then at this phase you can see even the voice coil that is pushing towards the fingertip to provide the feedback. So thanks to this design choice, so we obtain relevant characteristics. So in this case, all the mechanism is shaped around the finger. So all the bulky parts are aligned toward the length of the finger. So in such a way that it is not as compact as the other device, but it is not perceived. It is more dimension because it is beaded around the finger. Then, for doing that, we need to accurately design the joints for the function that they have, because all the joint axes of these kinematics are crossing the finger. So of course I cannot put pins inside the finger. So that requires the designing of all the parts of the joints, with difference of the other approach. And in this case, we perform a custom design of the voice coil, so the last actuator that is integrated in the last joint. So that wood part, it is the custom actuator, and so the fact of putting a voice coil at the hand as a last actuator with a direct actuation to the finger pad allows us to provide even not only a static force or a slow adapting force, but even a high frequency vibration for texture and sleeping rendering. So we haven't integrated yet this feature, but the mechanism has the capability to do that. So for doing that, even the voice coil actuator has been designed in such a way to have the better characteristic at the end of the stroke when it is touching the finger pad. Even in this case, so we have the specs of the device are similar to the other device. It seems bigger because of the length, but actually you have the finger in this dimension, so it is not as much bigger. And the weight, it is higher only because of the presence of the voice coil, but we have an extra feature because of the vibration for that. So it is an extra cost that is it worth to have that extra grams. And here you can see the same displacement for the translation degrees of freedom, but much higher range of motion for the rotational joints. Okay, that's it. Thanks.